morning, everyone, and this is going to be the exam review for 2414. Today, I mostly just wanted to go over, like I said, like tips and tricks, basically. Like these, integrals can take a long time as problems, so I just want to introduce some things that might shorten them, and also just go over topics that I've noticed and people have confusion with. So the first thing I actually wanted to cover is I noticed that a lot of we see this integral a lot, right? Integral of secant cubed of theta or x. And I noticed that it can be kind of a tricky one to do, but not only that, it often shows up inside of other integral problems. So I wanted to briefly go over how to do it, because we can learn how to do it quickly, and maybe if it's even part of a longer problem, maybe we could also just memorize the formula to it, because I think that would be helpful. So when we're doing this one, the way we always start off is, we have integral secant cubed of x. We can always break it up into secant times secant cubed, or secant squared, right? From there, secant squared always decomposes into 1 plus tangent squared, which is nice because when I have an addition or subtraction within an integral, I can break the integral up along that addition. So that's what I do. This becomes integral of secant plus integral of secant times tangent squared. From there, this one's pretty easy to do, right? Integral of secant, that's just the formula we should know. There, specifically, that's always what? Who remembers integral of secant? I guess we'll copy this down first. Integral of secant is always natural log secant of x plus tangent of x. Right. So from there, the harder part is doing this integral, the secant times tangent squared. To do that, we decompose it through partial fractions, letting u be tangent and dv be the remaining secant times tangent. All right, this should feel familiar. So integral dv is secant, derivative of u is secant squared. So we write it down in the formula, u v secant tangent minus integral of v du secant cubed. And from there, the tricky part about this integral is actually, once we get to this step in the process, so right, we have our original integral, secant cubed, is equal to, right here, integral of secant, plus the integration by parts, secant tangent minus another integral of secant cubed. The trick with this one is that we actually have to add integral of secant cubed to both sides of this equation. If we do that, this and this cancel. And over here, I have this plus this, 2 integral secant cubed. So that leaves me with 2 integral secant cubed dx is equal to this integral of secant plus secant tangent. And so if I divide by 2, I get the final answer. Integral of secant cubed x equals this, integral of secant, natural log secant plus tangent, plus the secant tangent from before, all over 2. But what ends up being nice about this formula is that we notice, if we look at the answer we get, the first part of it right here, that's always equal to natural log of secant, right? Just integral of secant, right? And the second part, secant times tangent, well, that's equal to what? The derivative of secant, right? So what we can say, if we want to shorten it down, is that the integral of secant cubed equals exactly the average of secant's derivative and secant's integral. Which is nice, because if we just memorize that, that means we can avoid doing, this long process of, well, not too long, but, this kind of tedious process of integration by parts and then adding over. Normally, I don't recommend just memorizing like certain integrals, but with this case, this one appears like quite frequently in the problems, so I think it might be helpful, especially if you're like running short on time in the test. Okay, so we all good on this page? All right. I also wanted to briefly go over surface area of rotation. We didn't cover that in the last class, but I know it's also going to be in our exam. So, and the one thing I really want to talk about is that we set the integral up differently depending on two things. Which axis you're rotating around, right? You can either rotate the, if I have some curve like that, when you're forming the surface area, you can always either rotate it around the y-axis or the x-axis, which will, always produce different rotations. But it also depends on how the function is presented to you. You could be given x as a function of y, or y as a function of x. We're more used to seeing this, y written as a function of x. But in problems, they might also give it to you like this, x is a function of y. So just making this little chart, I kind of want to just demonstrate how you write the entire integral formula based on these two pieces of information. If it's in blue, that means it's because of what axis you're rotating about. Essentially, the outside part is always going to be the variable that's opposite your axis of rotation. Side variable. Opposite. Rotation. All right, and on the inside, so the formula is square root 1 plus slope squared. This slope depends on what form the function is in. So if it's a normal function, like y as a function of x, which we traditionally see, we use the normal dy dx, right? Derivative of y with respect to x. And then the whole integral of dx. But if it's reversed, if we're in the form of x as a function of y, we use the opposite. Derivative of x with respect to y, dy. Okay, do we have all that? All right, let's move on to an example. So let's say we're finding the surface area of rotation for x equals, or, x equals e to the y, for y between natural log of 2 to natural log of 5 about the y-axis. So when I'm doing that, we need to ask ourselves, about which axis are we rotating? Y, right? So what variable goes on the outside? X. It's right, it's always opposite your axis of rotation. So in this case, I put x as a function of y on the outside. Oh, 2 pi, of course, sorry. I put 2 pi's in the previous, yeah. Cool. And now, are we dealing with the form x as a function of y, or y as a function of x? Or maybe I should say, what are we taking the integral with respect to? As x changes or y changes? Y's changing, right? So dy, and then the slope will be, right, dx dy. Yeah, and finally, just write down our bounds. What is y going from?
2.
Right, natural log of 2 to 5. Cool, and just to set things up, over here. So if x is equal to e to the y, what is dx dy equal to? E to the y, right? It's its own derivative. And so let's see. So in our problem, the x on the outside, since I need to rewrite it in terms of y, because that's what our integral is in terms of, right? Well, x in terms of y is just this, because that's what it's equal to. So the outside becomes e to the y, 1 plus the derivative, which we said was e to the y squared. I'll just make a note. This was x rewritten in terms of y. So now we have an integral. How would you go about solving this one? Hey, morning. Any guesses for how we should try to start solving this one? Well, she's blue. This one we can actually start off with the u substitution, where we can let u equal e to the y. If that's the case, what does du equal? Right, e to the y dy. And if we rearrange that, we get d of y equals du over e to the y. So, plugging that in, I'm going to ignore the bounds for now because u substitution has changed them, and we'll write our integral as 1 plus e to the y squared. dy has become du over e to the y. And so we notice that now, as written, e to the y and e to the y can cancel. And we will have 1 plus, remember, u is equal to e to the y, so u squared du. So now, how would we solve an integral like this? Square root 1 plus u squared.
Arctan?
U equals arctan?
Oh, no, we're doing that. Just tangent.
Yeah, I think that'd be the case. We can say, for ones like these, when it's square root like a number plus u squared or x squared, it's generally going to be a trig substitution. We can go over the formulas for those, but when it's one or a number plus the variable squared, it's usually we're letting the variable equal tangent. And so if that's the case, what does du equal? Right, secant squared of theta. So I rewrite my integral. U is equal to tangent, so tan squared of theta. And then du becomes secant squared of theta d theta. All right, and so based on our formulas, what is 1 plus tangent squared going to become? Secant squared. And square root of secant squared is just secant. So secant theta times the secant square root of theta d theta gives us 2 pi integral secant cubed of theta d theta. Which, if you remember the formula from a page ago, you could go through the work with this on the test, but integral secant cubed is going to be what? The average of secant's integral plus its derivative. Cool. So if we plug in, what's the integral of secant?
Natural log secant plus tangent.
Right. That plus derivative of secant, which is secant tangent. Cool. And the very last step for these, that now we have to just, plug back in our original substitutions. So, if u equals tangent of theta, which in terms of triangle side lengths, what is tangent of theta? Like SOHCAHTOA stuff. It's opposite over adjacent, right? Opposite over adjacent. So we can say, because that's what u is, so we can say u over 1 is opposite over adjacent. So, opposite adjacent by Pythagoreans, that would have to be that. Is everyone familiar with this method for, resolving trig integrals? Okay, cool. So then secant, which is, again, secant's the flipped cosine. So if cosine's normally adjacent over hypotenuse, secant is hypotenuse over adjacent. Which in our case is square root u squared plus 1 over 1. So plugging in, we're going to have natural log of secant, which is this, square root u squared plus 1, plus tangent, which we know is just u. So, right, natural log of that, plus secant, which is square root u plus 1 times tangent u. And while I'm here, let me cancel out these 2's. Cool, and then the final step is, we remember, what was our first substitution? We let u equal e to the y, right? So that means we have to take this one and now plug it back in to get in terms of y again. So natural log of, let's see, square root u squared plus 1 is e to the y squared. It's bigger. Natural log square root e to the y squared plus 1 plus e to the y plus square root e to the y squared plus 1 times e to the y. And we know our bounds are from natural log of 2 to natural log of 5. But since plugging in is not really the hard part of the integrals, we can go over this at the end or after other questions if you prefer. Oh, well, okay, so. Anyone still need this page, or? Okay. I also just wanted to briefly review the strategy for tackling rational polynomials. So. And just to review, so a rational polynomial, when I say that, it's just any integral where we have some polynomial degree n divided by another polynomial. And this doesn't include things that are all raised to like some single power. So like if I had square root of an entire polynomial, that wouldn't be like this type of thing. Those are slightly different methods for solving. And so the way I like to think about the options we have here are one, top polynomial has higher degree. So in our examples, that would be this first one right here. So who remembers the general method we want to try when the top polynomial has a higher degree? Right, we try. So in this example, we'd have to divide what? X cubed minus 3x plus 13 by x plus 3. So we set that up. Remembering that it's helpful to backfill in the missing terms. So in this case, this guy doesn't have a degree 2 term, so I just add 0x squared. And if we do that long division, so what's the first multiplier that goes on top? X squared, right? So x squared, and this becomes x cubed plus 3x squared. subtract, and we'll get negative 3x squared. Cool, what should our next multiplier be? Right, negative 3x. This times this. Minus 9x. Subtract, and we get what? 0. And then, let's see, minus negative 9. So plus 9 minus 3. 6. And then the final multiplier is positive 6, so 6x plus 18. Cool, so we get a divisor of x squared minus 3x plus 6, and a remainder of negative 5. So I can rearrange that as saying this fraction equals this plus negative 5 over the original divisor. And then this is a fairly simple integral to do. First term will be 1/3 x cubed minus second term 3 divided by 2 x squared plus 6x minus 5 times the natural log of x plus 3. Okay, and in the case that we have the bottom polynomial having a higher degree, what method should we try then? If the bottom polynomial is a higher degree, then we try what? Partial fractions. All right, so starting with partial fractions, the first thing we always have to do is fully factor the bottom. So in this example, what does x to the fourth plus x factor into?
X and x cubed plus 1.
Right, the easiest term to first factor out is x cubed plus 1. Dx. Which is now fully factorized. So that means we can always rewrite the inside as what? The sum of fractions over those individual factors. And just a reminder that the form of the polynomial on the top is what? Degree 1. All right. Right, the form of the polynomial, it's just a polynomial that's degree 1 lower than the bottom. So in this case, a degree 1 polynomial has a degree 0 or constant above it, and a degree 3 polynomial has a degree 2 polynomial above it. And so from there, we just cross multiply to get everything to the same base. Which means we can set our original equal to the original fractions numerator. And finally, separating by variables, let's see, we get ax cubed plus a plus, let's see, distribute the x, bx cubed plus cx squared plus dx. And so now I can set the degree, the coefficients of like degrees equal to each other. So in this case, this degree 3 coefficient, a plus b, equals this one, 2. Same over here, c equals 0, d equals 0, and then constants equal constants, so a is -1. Which, if we plug it back into here, we should get b equals 3. And so finally, just plugging back in, we have a over x, so -1 over x, plus bx squared, 3x squared, plus 0 plus 0, over 1 dx. And I'll leave this one for you guys to solve, but now this is much, now it's in a much simpler form. All right, any questions? This one, okay, good. Can I turn the page? All right. I also just wanted to go over like a few integrals that I saw people kind of coming into math lab over and over again for. You personally may not find some of these tricky, but these are just ones I've noticed people having some general trouble with. And before we start, I'm just going to make a note that the method will also work for sine of x Okay, so is anyone familiar with this one? Do we know how we get started? One thing that's often useful to try is that when we have a square root, especially a square root of something like like a simple additive term, like 1 plus a function of x or 1 minus a function of x, generally a good thing to do is multiply the top and bottom of this integral by this thing's conjugate. So in our example, that would be 1 plus cosine of x. All right. So algebraically, how would the top two terms combine? If I had square root 1 minus cosine times square root 1 plus cosine?
It's just regular distribution, isn't it?
Hmm?
So it'd be 1 times 1 and then 1 times cosine x.
Right, they have the same exponent, so I can just FOIL them as normal, keeping them all under 1 square root. So 1 minus cosine of x, 1 plus cosine of x. And remember, this trick only works because they both have the same exponential powers.
But this square root not cancel because you're multiplying it by the square root.
That's only if it's the same term on the inside.
Oh, gosh.
These are two different terms, so they actually don't have that. But they can still come together like this, under 1 square root. And so we see the inside on the top is essentially just a difference of squares. So what does this difference of squares simplify into?
1 minus cosine squared x.
Right, 1, which is 1 squared, minus cosine squared of x. And so maybe some of you see where this is going. What's 1 minus cosine squared of x? Right, so square root sine squared, sine of x. And then from there, this one can actually just be solved by a simple u substitution. Anyone know what u should be? Or have a guess? 1 plus cosine of x. So that means du will be negative sine of x dx. Or as it's rearranged, dx is du over negative sine of x. But regardless, we have sine of x over square root. Oh wait, no. Which we can see cancel, cancel. And we have negative 1 over u du e to the negative 1/2. Right, just simplifying it to like this, a term that's easier to do integral on. And so finally, what's integral of u to the negative 1/2? Right. Right, so the negative 2u to the positive 1/2. Two being what happens when we divide by 1/2. Oh. Let's see, u is 1 plus cosine. So that's our answer. Okay, good on that one. Let's see, let's do I've seen people asking about secant tangent integrals. So let's see. Let's say we have this case. Secant to the 5th, tangent to the 5th. These can be a bit obnoxious because depending on which power secant and tangent are raised to, that actually changes what u substitution you want to use. Although in my experience, one of the easier ways to figure this out is, right now they're both to odd powers, right? Let's factor out a number of terms to make them even. So in this case, I just need to factor out 1 secant from here to leave us with what? Secant to the 4th of theta, right? And if we factor out 1 tangent from here, I have tangent theta. So this is tangent to the 4th of theta, d theta. And the idea is, whatever this new term I created is, I want my choice of u, its derivative to cancel out with that. So essentially it should equal derivative of u. So in our case, if secant tangent is the derivative of u, what is u? Secant. Right, because we can clearly see secant tangent d theta will just go away. So this and this term go to du, and we're left with secant to the fourth of theta, tangent to the fourth of theta. And if I rewrite everything in terms of secant, I get this u to the fourth, 1 plus u squared, all squared. And let's see, I'll leave that for you guys, but this is just another polynomial, right? We just have to FOIL it out, and from there it's as simple as doing any other polynomial integral. FOIL and solve. Sorry. So I want to save the last 15 minutes for like questions we have specifically about like anything we covered or the exam in general or
Can you do another problem on surface area?
yeah, of course. Anything specific? Were you here for the first one?
No, I walked in late, so I missed the.
Okay,
the-
we can go over a let's see. Would be a good one. Okay, let's try this. Y equals cube root of x from x equals 1 to 2 about the y-axis. So important things to make note of. We're about the which axis? Y. So which variable goes outside of the square root? X, right? So 2 pi x times 1 plus. And what are we integrating with respect to? Which variable is changing? X, right? So that means I go dy dx squared with respect to x. Oh, of course, from 1 to 2. Right. And if we solve it out, since we know that y is x to the 1/3, what is that derivative going to be? What? It'll be 1/3 x to the, excuse me, negative 2/3. So I squared this term, and what am I left with? Well, 1/3 squared is 1/9. And then squaring this, I just multiply the two powers together. So x to the negative 4/3. So this one, let's see. Let's see, for this one, I wanted to factor out. Oh, x. Okay, that should work. So if I just simplify it, make it to a fraction of same base. I can rewrite it like this, which allows me to pull out these terms from inside the square root. So this times the bottom term, the square and the square root cancel out, and I'm left with this x to the 2/3 integral. So let's see, that would be okay, yeah, so this works out. So x to the 1 divided by x to the 2/3 is x to the negative 1/3. And then if I factor out a 9 from both of these terms, I get what? X to the 2/3 squared plus 1/9, right, dx. And then from there, we notice this is an arc, or not arcsecant, this is just a secant form. Right, this is some variable squared plus some other number. So I can say let x to the 2/3 equal in this case, because that's 1/9, this will be 1/3 secant theta. So now we do the derivatives. What's the derivative of x to the 2/3?
2/3 x to the negative 1/3.
Right. Dx becomes, what's the derivative of secant? Right, 1/3. And what we can see is that if I rearrange the d term, I have x to the negative 1/3 dx equals all this. So that means this term and this term can come together to be replaced with this. So all that becomes, let's see, this and this, so that's just 1/2 secant theta, tangent of theta, and then square root 9 times, let's see, 1/9 secant squared of theta plus 1/9. Oh, I shouldn't be writing the bounds because we just did a substitution, right? Okay, so let's see. So times the 1/2 from the inside, integral secant theta, tangent theta. The 9 cancels out with these, and we're left with square root secant squared plus 1, which should just simplify into tangent once you cancel out the square root. And then from here, to do this integral, what'll actually end up happening is if you, let's see, where was it? In this example, we kind of talked about how if I wanted to figure out a good u substitution term, I need to factor out terms in order to make these remaining ones even, right? In this case, that's not really going to work because I can't tan's already even, and I can't really factor out secant anymore. So what actually happens here is that this guy, tangent squared, becomes, it's substitution, 1 plus, or secant squared minus 1, right? Oh, did I
We're not supposed to integrate, right?
Hmm?
We're not supposed to integrate, because we don't know x, the original x in the formula.
The what?
Because it's 2 pi x, right? But we don't know x.
2 pi.
In the very, very top. So I thought if we're doing the opposite, we're not supposed to solve the integral.
If we're doing the opposite,
Because we don't know x, right? You're not wrong.
we know x's range is going from 1 to 2.
No, 2 pi x in the formula.
2 pi x. What's wrong with that?
Because I thought we don't have the equation to plug in to that.
Well, yeah, but it's already in terms of x, right? Our integral. So we don't need to plug in an equation for this x. That makes sense. It's already in terms of the correct variable.
why are we integrating that? Because
Because the formula requires it. Does that make sense? Do you want to talk about it after the? Okay. Okay, okay, guys, I'm really sorry. If it's square root x squared plus a squared, right? What formula? You're not supposed to use sec, and you're supposed to use tangent, right? This method is generally correct, but this is.
Got it.
But does that make sense? Like we can also go over the general way you set these up too, because I know you weren't there for that.
No, it's okay. I get the process. Could you scroll up just a little bit?
Yeah.
You kind of lost me at the part where it was the 1 plus 1 over 9x to the 4/3. And how did you convert that to the next step?
To the next step, like from here to here?
Yeah.
Okay, well, essentially, let's hope I didn't make a mistake here too, right? 2 pi x. Basically, I just wanted to add these two fractions together. So first thing I do is I convert 1 into 9x to the 4th over 9x to the 4th, or 4/3. That plus 1 over 9x to the 4/3 dx. So let's see, tops add together, 9x to the 4/3 plus 1, and then bottoms come together, so x to the 4/3. So that was how I got to this step right here.
Okay, but then where's the 9 on the bottom?
Oh my god. Yeah, I'm sorry, I was rushing through this one. That was...
That's okay. That's where I was lost. I was trying to find the track from there.
Yeah.
I followed the rest, stepwise.
The rest makes sense?
Yeah, like I know what to do. It's just I got
That's
lost
bad,
in my
yeah.
fraction.
Okay, sorry about that.
It's okay.
That is a example. Okay. Or the any other questions you want to? Oh yeah.
Can we go on vectors?
Yeah, of course. What do you want to specifically about vectors, like visual representation, math with them?
The math part of it, like if it asks you to do like a over absolute value of a, like.
Oh, okay, yeah. What does that mean?
Yeah.
Okay, so that's actually very. So I guess first thing is. Are you familiar with just the notation like double bar absolute value of v?
Is that magnitude?
That's magnitude, right? Like the length of vector, which it's magnitude. And if I asked you to like find, I don't know, the length of this vector, 5, 5, -12. Would you know how to find that?
Is that square root of x squared plus y squared?
Exactly. It's the square root of all, and if it was a longer vector, like length 3-dimensional, it'd be the exact same formula. It's just the sum of all individual terms squared. And I'll just say for definition's sake, so in our case, that'll be square root of what? 25 plus 144, which is square root 1, 6, 9, which is equal to what? 13. So that's thing 1, and then thing 2, I'll say any vector divided by its own magnitude is called a unit vector. And what's special about unit vectors is that unit vectors always have magnitude of 1, which is to say, if I took the magnitude of this guy, v divided by its length, that would have to equal 1. So in our example, what is v divided by its own magnitude? Like, what does that look like? Do we know how we do that process? It's actually pretty simple. Like, it's not hard when you're multiplying a number by a vector. The way it works is, so first, what's the number we're dividing by? The magnitude of v is, we found it to be 13, right? So what I'm doing is 1 over 13 times my vector v, which is this, 5, negative 12. Right, so far so good? And the way it works is, if I'm multiplying a vector by some constant number, all you do is distribute the number to each of the components. And we say this is called the unit vector in the direction of v. It's basically a parallel vector to v that's exactly length 1. And if we want to check that, well, we know the length of this new thing we found is just going to be sum of the individual components squared. Which, we do the math, again, 5, and this time over 169, 144 over 169. So yeah, it checks out. Do you have any questions on adding vectors? Like if you had to add 2 vectors together, would you know how to do that?
It's just adding it, right? Like add
Yeah,
X and
just the
X.
2 individual corresponding elements add to each other. So first element, second, second.
And like the equation of the sphere, if you have like a point in the center, I think.
Right, that one's actually, just really quickly. So like, let's say we have a sphere, right? Not my best, but. I'm just going to derive the equation once, and then from then on, we can just remember the formula. But let's imagine we have a sphere whose center is very specifically some point x naught, y naught, z naught. So we have x naught, y naught, z naught is our center point. And let's say further, the sphere has a radius of r. right? What that tells us is, if I take any point on the surface of the sphere, and let's call the point just XYZ, right? No subs, just XYZ. What's the distance between that point on the sphere and the center?
The square root of something times something squared.
Well, even more simply, just going back to the definition of like circles, we know that, what's the length that connects the center to the outside? It's the radius. So same here, the distance between the center and any point on the surface is just r.
Okay.
So what that leads us to say is that the distance between point on the surface and the center, right, distance between 2 points, has to equal radius. And from here, it's actually just using the distance formula. So how does that apply here? Do we remember the distance formula for
Subtract used term of d squared.
sum of like subtractions? So x minus x naught squared, y minus y naught squared, z minus z naught squared equals r. And then the final thing people do is they square both sides. So if I were to do that, this square root would go away. That would become r squared. And this equation right here is what they mean when they say standard form of a sphere. Given this center and that radius. So when in doubt, you can always derive it, but that's, it's essentially just like the distance between the center and the point on the surface. All right, cool. Anything else you guys want to go over? Feeling good? Okay, cool.